Okay, thank you very much. Now, maybe I should start with an apology because I should really be talking at the end of this because I'm going to build on ideas that just have been presented on the last few slides you've seen in Daniel's talk, and then will continue to be elaborated on tomorrow. So in that sense, it's a bit unfortunate that I'm not quite at the end, but unfortunately, I will not be here tomorrow. So this is why I'm now going to talk about holography and black hole entropy. That is how ideas coming out from black hole thermodynamics have been extended into even more speculative ideas, into ideas about holographic theories. I'll explain what that means. Okay, I will rely in my presentation primarily on these sources. So this is Bekenstein's original argument for an entropy bound from 1981, then a popular article by him, a review article by Raphael Busso, who has recently contributed to quite a bit of that literature, then papers by Gerard Huthoeft and Leonard Susskind, who have made that leap to a holographic principle and holographic physics, and Lee Smolin, somebody who's outside, unlike some of these people, well, Susskind for sure, outside of string theory, that have nevertheless used some of these ideas in their approaches to fundamental physics. So the starting point is, in some sense, where Daniel left off. It's black hole thermodynamics. So I'm going to present three central ideas and assumptions that I will presuppose for now, but which are, each of them, physically substantive and certainly should not be accepted without further confirmation, and really be convinced that these are true propositions, true things to say about the physics of our world. The first one is the so-called generalized second law. That's in the usual thermodynamic counting of laws or ordering of laws. It starts out from the idea of a second law, such that entropy of a thermodynamic system can never decrease, but it generalizes it to include the idea that black holes are objects which also have entropy. Moreover, they don't have any of the other kinds of entropy, some entropy that's distinct somehow from entropies of thermodynamic systems, but it is really the same kind of entropy because it can be meaningfully added to a total entropy, as it were, such that you can then articulate a generalized version of the second law, which asserts that the common entropy in the black hole exterior, so that's the usual thermodynamic entropy that you have of all the objects which are outside of the event horizon of a black hole, plus the black hole entropy now as a total never decreases. So you can throw packages of entropy into black holes and do things like that, but that's not going to violate this generalized version of the second law. So this is one idea which I assume will be talked about more tomorrow. The second idea is that of black hole entropy more specifically now, because that seems to be necessitated by this assertion. I need to say something about what this black hole entropy is, and in particular, how I can compute it. What is it? Here's this second statement I will need. The black hole entropy S sub H BH, which can be read for black hole or for Bekenstein-Hawking, if you prefer, or some such thing, is given in Planck units, which I will use. You set conveniently all the boring constants to 1. You forget about that. You just look at what's relevant. And you see that this black hole entropy is just a quarter of the area of the future event horizon that we just, so this formula, maybe not quite as prominently as here, was on one of the last slides from Daniel. It was, I think, when you, in the thermodynamic laws, it was somewhere there. Okay.
Can 4 also be set equal to 1?
Yeah, well, maybe. I don't think so. I mean, look, that's not really where the interesting physics is. Of course, you can choose your units such that this will go away. What is really important is that this entity, this quantity here, the black hole entropy scales with the area of the event horizon. That is really going to be the central idea of which we will make use here. Okay, and the third idea, which I'm not going to present. If you followed Daniel's course, crash course into GR, you should know. Otherwise, you can go and read it up in these two standard textbooks. It's an implication of GR, which I'll call gravitational collapse, namely the idea that if you take a system of some mass, well-defined mass, in the case of black holes, maybe ADM mass or so, but I'm not going to worry about that, some well-defined physical mass, and you pack that into a too small area, spatial area, then it will collapse into a black hole if you confine it to within its what's called Schwarzschild radius, which is given by this formula. So that's a direct function of the mass. Ooh, shoot. That was not a good idea. Okay, increasing entropy here. Okay, anyway, these are three ideas which deserve to be elaborated further, which deserve to be justified, but I'm going, for the purposes of this, going to start out from them and see where physicists have, in what directions they've developed them. Okay? So let's start with Bekenstein, 1981, which is really, I think, where it starts. Here's a quote from him. He complains that two obstacles really stand in the way of attempts to understand this mysterious connection between area, which is, of course, a geometric quantity. So Hawking's area law really is a geometric theorem in GR. It's a statement about the geometry of black hole spacetime. How could that be so closely linked or even identified with entropy, thermodynamic entropy, with a thermodynamic quantity? So we heard this morning from Aurélien that there are all sorts of deep connections between geometry and thermodynamics, but it's certainly not obvious. It's certainly prima facie very mysterious that these should be the same sort of things. Now, I think there are many reasons you could be suspicious of that connection. Bekenstein gives us two reasons to hesitate to make that connection. The first one is that it seems that black hole entropy is numerically so much larger than the entropy of any ordinary system of like mass, such as, for instance, a solar mass black hole has a black hole entropy which is 10 to the 20 times the sun's thermal entropy, roughly speaking, which is much, 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 much bigger. So it seems like, I mean, what's going on? Why would, should that be sort of the same thing if they're sort of really at very different scales here? He thinks it may be considered preposterous even to think that there's a common denominator in these two quantities, so unlike in size. Okay, good. So that may be one obstacle in making that connection. The second one he lists is that even if these two entropies are of like origin, how can one hope to express black hole entropy in statistical terms when that task evidently demands a full accounting of all that could possibly happen inside the black hole? So we would have to find, and it seems, just like for an ordinary thermodynamic system, like a gas or something like that, we would need to find some meaningful way of doing some sort of state counting. So we would have to know more about the black hole physics and what the different states can be. It seems like the picture that general relativity is giving us of a black hole is too impoverished really to permit that. So as you've seen, for a very, very large class, there's excellent reasons to believe that a black hole is exhaustively characterized in GR by just three quantities: mass, angular momentum, and charge, and that's it. How are you going to do some interesting sort of statistical physics with that? It seems like we will have to learn more about black hole physics before we can do that. Now, that's mentioned, but just as Bekenstein 1981, I will not worry about this second thing. This is for future considerations, but I'm going to address, like he does, the first concern. Okay. And that is really where this idea of entropy bounds comes up for the first time very, very explicitly, at least as far as I know. So he asks, is there something that we can say that is quite general about the relation between a space-time region, which clearly is characterized by some geometry, and the thermodynamic entropy of a system that contains, that occupies, I should say, that region. So that you can maybe, because it's so general of what you're going to say, you can hope to make some sort of connection between the geometry of the space-time region occupied and that generic physical system and its thermodynamic entropy. So that's the starting point. And specifically, you would like to know whether there exists some sort of entropy bound, a maximum entropy that you can, such a system could have if contained in a finite region. In other words, I give you a finite spatial region, and you try to do whatever you want, whatever physics you want. You take any physical objects, anything physical, and you try to maximize that entropy that's contained in that region. Another way of asking the same question is, how can you really densely pack states of a physical system such that this quantity becomes very large? What's the best you could possibly hope to do?
If you do that, and at the end of the day, you also take into account the fact that the actual geometry of the region and the size of the region will be affected by the effect of the mass on the geometry.
Yes, it's going to turn out to be complicated, and we will have to make some simplifying assumptions to get anywhere. But yes, that's certainly a concern, absolutely. Okay, good. So what does Bekenstein do in 1981? Tim?
Quick comment, because I don't think you're coming back to it, just for some things people would talk about. You said, well, look, you have these no-hair theorems or quasi-theorems or whatever you want to call them, have not been proven, that say that as far as an outside observer is concerned, the black hole is characterized by just three numbers.
Sure.
And that you present it as problematic for understanding this huge entropy. But one can turn that around and say the Boltzmann entropy is the volume of phase space that's consistent with the macro description. Mm-hmm. The less information in the macro description, the more generic it is, the bigger that phase space is going to be, and the bigger the entropy is going to go. Mm-hmm. So
okay.
That way,
then it's less mysterious.
Very simple description is the macro description, mm-hmm. Then the fact that the entropy goes through the roof is what you'd expect.
Mm-hmm. Okay. Yeah, so maybe this is a mistaken project in some sense, or the motivation for it anyway may be somewhat mistaken if you think about it differently. So I don't think this is the way that Bekenstein thinks about it. This is why he's concerned with the question. But the point is taken. Okay. First of all, if you do this, if you come to this question now of whether there are entropy bounds like that from classical physics, Newtonian physics, you'd think, why should you think that there's a limit somehow to the entropy that you could pack into a finite volume? You wouldn't think that there really should be one, because there's no reason to think that you couldn't pack your physical system however densely you want. All these states, pack them as you want. And, there's no reason to think that somehow the energy would have to be bounded. In principle, it could be beyond any bounds. And so, presumably, the answer that classical physics gives you without further consideration is infinite. You can pack an infinite amount of entropy into a finite volume. Now we know classical Newtonian physics is not true, so we shouldn't give too much on that. Let's at least take one further step and sort of look at some field theoretic approach. What would field theory now tell us would be the maximum that we could? Quantum field theory in particular, because that seems to be the best framework to understand the constitution of matter. So why don't we look at what that theory will tell us? Now, quantum field theory seems to suggest also that there is no such bound, because a space region or space-time region in general has, of course, an infinite number of degrees of freedom, infinitely many states, simple state counting argument, you get to the conclusion that the entropy should be infinite again. So if you have a regular sort of standard plain vanilla quantum field theory, there's no reason to think that this should be anything less than infinite. Problem solved? Question answered? Well, no. Bekenstein clearly doesn't think so. Why not? Well, he gives us essentially, that's the point of the paper, an argument that this conclusion is false, that we should believe that there's a finite entropy that can be packed into a spatial volume. And he gives us an entropy bound that's now, he calls universal bound, but people in the literature usually refer to this now in honor of him as the Bekenstein bound. There it is. At least for weakly gravitating matter systems in asymptotically flat spacetimes, there exists a universal upper bound of this magnitude 2πr, where r in Planck units is the size of the assumed to be spherical volume, spatial region, not the entropy, but the entropy per energy of any arbitrary system, and this is the bound he gives. Now, I'm not going to bore you with the reasoning he goes through. He gives a couple of arguments. He looks at different kinds of matter and gives us some sort of plausibility considerations to think that this is a reasonable thing to think, that these are all bounded by that bound here. And he also looks at different types of matter, because presumably how densely you can pack states depends on what kind of matter you look at, whether it's a liquid like water or something else, et cetera, et cetera. Presumably that answer could be something different. So he looks at some different cases. And he makes some important assumptions, namely that gravity is sufficiently weak throughout the whole process here. So, for instance, that you can have a meaningful time foliation, the system is at rest, so you have a stationary solution, and the space is almost Euclidean, nothing screwy sort of is going on with the geometry. Now, of course, that seems to be a severe limitation of any of these considerations, whatever they are, because if we've learned anything from GR, then that doesn't sound like something we should blindly trust if we pack some sort of material very densely. David?
Chris, could you just, I know you don't want to go into the arguments with this formula, but is there a way to indicate just in a line what was too quick about the original field theory argument?
I'm going to get to that in some sense. I think what's too quick about it is that if you make some sort of minimal assumptions about or here's how I should put it. If you accept some minimal implications of GR, that when you densify these things, then there will be something like gravitational collapse. So, it seems like, then it can't really be infinite, or, and then we have, that's what's going on in the background here. I think without that, I don't think, you could really say in any meaningful say that that was too quick. Then it seems like, well, that's what you're going to get, the answer you get.
The framework is standard GR?
It's not really standard GR or very much from GR, other than the idea of a gravitational collapse and the formation of a stationary black hole if you pack things too closely. So usually it's more about the physics of the matter than really the GR of the space-time background that goes on in these papers. And that doesn't change when we go to later people like 't Hooft and Susskind and people who have contributed to that literature. Now, there are exceptions to that. People like Raphael Busso, for instance, very much then take it much more seriously, the GRs than the geometric side. I'm going to mention that as I get there. So I think Eddie was next.
Yeah, to go back to the previous slides, the field theory argument. So, just to get clear on this argument itself. So, for the classical, mechanical state space, there are even many states. But then the state space is one-dimensional. So there is a measure in which the volume of the maximum state is finite dimensional. finite. Right? So here, the problem is a problem that even dimensional degrees of freedom is not because there are even many states, but because there's no good measure according to which the entropy is finite. But even the many states itself is not sufficient for them to be a problem.
So that there, sorry, I'm not sure I understand that the fact that there's infinitely many degrees of freedom in a finite region, that's not a problem?
No, I think here's what Eddie's saying. You go back to Newtonian mechanics.
Oh, so not this slide, not the quantum field theory.
But just to compare it with this slide.
Okay.
We calculate entropies by volumes in phase space. So it's not really, I mean, we're counting the number of states only in that loose measure sense. And that we're calculating volumes of phase space. The minute you go to a field theory, either a classical one or a quantum one, then you're dealing with an infinite number of degrees of freedom.
Yes.
Not just an infinite number of states.
Yes.
So the state space you're dealing with is infinite dimensional.
Yes.
And Eddie's worried that because we don't know how to put measures on those things, or because there are problems about putting measures on those
Sure.
things, we don't even know.
Okay.
Right.
Maybe I shouldn't have said it here because I'm going to come back to quantum field theory and the way you can come up with maybe a more reasonable way of counting states and giving some sort of finite answer to that question. Even then, it seems that there's going to be some conflict with what I'll call a holographic theory. But let me press on, because otherwise I really don't think I'll get anywhere interesting. Now, you can think for one type of matter, there's going to be this and such a bound, right? You just can't pack it any more densely than such and such. You're going to have at most such and such an entropy per volume. For other materials, maybe you can do better, etc. So it's going to be a sort of a material-specific answer to the question. And of course, you can then very naturally ask, well, what's the best you could do in principle with the best sort of material, as it were, for that sort of purpose? And that's going to give you the holographic bound. And this is really discussed only a little bit later, not in the original Bekenstein. So you can make the following distinction between a Bekenstein bound, which is a bound for entropy for a mass of some effective radius r, which depends on the density of the matter at stake, and a holographic bound, which is a bound for entropy of a mass of the limiting density of a black hole, which seems to be you couldn't do any better than that. You couldn't pack any matter more densely than that, at least if you accept that there would be gravitational collapse otherwise. As I said in the beginning, we will. And then the claim is, the holographic bound is, the entropy S in Planck units of a system is bounded from above by a quarter of the area A of the circumscribing surface, because that's the entropy of a black hole, and you couldn't possibly pack any more entropy into a spatial region than that. So it gives you, it's sort of a saturation. That's the sense in which this is the best bound you could get. Now, what's the argument for that? Why should we believe that? I'm trying to be a little bit more careful here than what you find often in the physical literature and try to really give you the explicit argument for that. I will take some hints from Lee Smolin. Here's Lee Smolin. He says, consider any physical system made of anything at all. Let us call it the thing. We require only that the thing can be enclosed within a finite boundary, which we shall call the screen. Okay, figure 39, here it is. So you're supposed to imagine a physicist who looks at the thing through the surface of the thing. Now you could think, well, of course the physicist could go to the other side and look at the thing from the back, right? Well, just think of the surface as the spherical surface of that region. Wherever you go, it seems you have to look through the screen to see the thing, okay? That seems to be the idea. So we would like to know as much as possible about the thing, but we cannot touch it directly. We're restricted to making measurements of it on the screen. We may send any kind of radiation we like through the screen and record whatever changes result on the screen. The Bekenstein bound says that, actually the holographic bound says that there's a general limit on how many yes-no questions we can answer about the thing by making observations through the screen that surrounds it. At no time can we know more about the thing than the limit imposed by the area of the screen. And at this point, for all of you, there should be the alarm bells going on. Beep, 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 beep. This is exactly the mistake that Tim has warned us before lunch. You know, this is completely confused, talking of what we can know and information and recording and stuff. No, 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 we're not talking about astronauts falling into black holes and what they experience, and astronauts not falling through the black hole, what they can know about their twins falling into the black hole. No, we're talking about black holes, physical objects. We want a completely objective physical theory of these things that have nothing to do with some sort of epistemic understanding of entropy or any information theoretic understanding. So I'm going to cleanse all of these arguments from any information talk. And I believe that much of it can really be done quite directly without any invocation of these problematic features. Physicists more and more seem to believe that just as biology is the science of life, physics is the science of information. I think that's completely wrong. It is not. It's so I think we should resist that. And yeah.
Sorry, just one comment, because whenever people, even before talking about information or any of those things, I think it would be very good to present more precisely the context in which one would hope to believe anything of that sort holding in the following sense.
Oh.
Let me take for as an hypothesis that our universe is closed. Something like Einstein's static universe, maybe not static, but it's a closed object. Then any surface, I mean, when you put it in terms of volume, I can understand and I may believe or not believe. But when it's framed in terms of surface, the point is that any two-dimensional surfaces can be thought as bounding the very small, tiny area region inside, or, when viewed from the other point of view, bounding the huge rest of the universe by exactly the same area. So what do we mean by this area enclosing the object? Is only the small one and not the big one? Or
yeah, good. Good. It's so, I mean, I'm relying on ideas in your lectures here. So suppose we have a well-defined notion of a black hole and the black hole event horizon and the area of a black hole event horizon.
so we're thinking asymptotically flat conditions?
Yes, so that's
Flat conditions, that's the regime we're in?
yes, that's the assumption. I think it was one of the slides beforehand, and if not, let's restate it. I'm assuming asymptotically flat space-time, so I assume that I can somehow isolate the system that I'm interested in. The thing is an isolated, isolatable physical system, and the physicists are, you know, far away and don't disturb the physics of that. So, and there's a clear inside now and outside.
So you're rejecting two asymptotic flat regions. You are rejecting a box of gold kind of things. All of those situations are not to be considered.
Yes, not for the time being. Now, the question, of course, is whether any of this that is developed here will be generalizable to other situations. And some of it is generalizable in a mild way, and other things are not. And for other things, it doesn't really even make sense to use the concepts here. But let me try to give a really relatively pedestrian introduction of what the general idea is here, without any information theoretic sort of argumentation or conflation. This is doing thermodynamics, not information theory. So a cleansed argument then could look something like the following. We have a physical system, any physical system you like, with some entropy S, contained in some finite spatial volume V, which I'll also call the bulk, which I assume to be spherical. I take that to be a relatively harmless assumption. That is bounded by a finite surface area A. So this is the picture you're invited to have in mind. Any sort of system having some sort of thermodynamic entropy, which is confined in a spherical volume with a surface area. Okay. Now, the argument to the conclusion of a holographic bound could take the following form. We assume first that the system in the bulk can be described by quantum mechanics. After all, quantum physics is our best theory to describe the constitution of matter, so we'll certainly start out from that assumption. That's substantive, but I take it relatively uncontroversial. You have a problem with that?
The problem is this. I mean, I thought the original formulas for recognition that there's a black holes behave thermodynamically in some sense is purely classical general relativity.
Oh, yes, but I think Daniel is going to talk about this tomorrow. The problem is, if you just look at general relativistic black holes, the only consistent temperature you could assign to a black hole would be 0, because they're perfect absorbers. They don't radiate anything. So you can just, it can swallow heat, but it cannot emit heat, as it were.
From a purely classical point of view, the mystery that you get this thermodynamic-like behavior, the area increase law.
Yes, that is perfectly classical.
Just an accident from a classical point of view. It's not going to be, you're not going to explain it in thermodynamic terms at all.
Exactly, and this is why before 1975 or so, physicists have not taken Bekenstein's argument very seriously. They've just said that, like, yeah, you found two things which both tend to increase or increase strictly, and you say they're the same thing. But why should we think that the area of the event horizon and thermodynamic entropy are really the same sort of things? In order for that to really get any traction, we would have a much fuller physical analogy between the thermodynamic case and the case of black holes, which includes systems which can equilibrate, systems which can have some sort of thermodynamic exchange, and these sort of things. And only once we could have the analogous of all these sort of physical processes, which we believe to be possible in thermodynamics, would we believe that black holes are truly thermodynamic objects. And I think you're going to say more about that. So you need something more than classical GR, and that something will have to be quantum.
But here the quantum is just for counting states or for something else?
Yeah, now that you say that, I'm
states and compute classical volume in any case, more or less, classical phase volume.
yeah, so maybe it could even be done without that assumption.
You're going to count states. Quantum states, energy levels.
Actually, only at the later point. So maybe maybe ignore this for now. The system, the second, however, seems to be important. The system in the bulk is sufficiently large so it admits of an average macroscopic description. So we have a macro variables and some sort of micro states. That's certainly what's needed. And I assume black hole entropy, which I've defined at the beginning. So that's assumed that black holes are thermodynamic objects with a thermodynamic entropy. I assume now for reductio, because that's the structure of the argument, I'm going to say for reductio, suppose the entropy of the system at stake is larger than a quarter of the area of its circumscribing volume. Then from black hole entropy, a black hole that could be fit into that same volume can have at most an entropy of a quarter of A. It could, of course, have less if the black hole would be smaller. That's possible. But at most, we get a quarter of A. Okay? That seems to imply pretty directly from 4 and 5 that the system, whatever it is, in that volume is not a black hole. Okay, fair enough. It's not a black hole. It's some other system. The system in the bulk, therefore, has less energy or mass than a black hole would that would just fit inside the boundary. Because otherwise, because of gravitational collapse, it would collapse to a black hole. That's why the collapse idea is important. Okay, so if that's the case, then it seems we can slowly add energy through the boundary. We can feed it some mass or energy through the boundary, through A, through that surface, to the system in the bulk. We need to be a little bit careful here that whatever we do doesn't upset the geometry of the situation or anything else that we've assumed to be held fixed. So let's suppose we do this very slowly, very carefully by small amounts. But however we do it, however careful that may be, there will be a point at which it collapses into a black hole, because that's what gravitational collapse asserts. Yes, exactly. That's true, that's fair enough. But assuming that, yes, whatever we fed into that region never comes out again. Okay? So at some point, this will have to collapse to a black hole, because now it reaches the density where this is unavoidable. Okay. Now, once that has happened, though, the collapsed system's entropy must now be a quarter of A, because it now is a black hole that is of that size. Okay? Now that means from 4 and 9, the system's entropy has decreased, because it was assumed to be larger before. After the process, it's higher. That is, however, violating another assumption we're making, namely that of a generalized second law. Therefore, by reductio, I get the conclusion that whatever the system's entropy is, it has to be smaller than or equal to a quarter of the surface size. So I didn't really use quantum mechanics for state counting in that simple argument. Okay, that's the general idea. Why some people have thought there must be a holographic bound, some sort of, however carefully you pack the entropy, or pack states into a system, however carefully you're going to do that, if you accept some basic facts about, some basic assertions, I should say, or propositions from black hole thermodynamics, and some implications of GR, it seems you are forced into this result. Yes, so Alex.
See what role this second assumption about averaging plays in this argument in the second premise.
Oh, so okay, good. That was a bit hidden here, but the idea is that we can have, before it's a black hole, the system has a well-defined thermodynamic entropy. Maybe I should just have said that, rather than anything else.
And is it clear, as you would expect it to be, that the generalized second law says that throwing in stuff to the black hole could only increase the entropy, not decrease it?
Yes, I mean, I think that's the way you should interpret the generalized second law. However, whatever physical processes there are involving black holes, it can never be such that the final state has a lower entropy, total lower entropy, the sum of the ordinary and the black hole entropy than it had before.
There's some compensation someplace else, which it doesn't look like there would be.
Well, but I mean...
No, but this seems to be asserting that there couldn't be. I mean, that's what... In ordinary thermodynamic systems, if you have two systems in thermal contact, a hot system and a cold system, of course the entropy of the hot system can decrease, but that's because it's being more than compensated for by the increase in the entropy of the cold system. Here, it doesn't look like a black hole is going to be that kind of a participant in thermodynamic exchanges, because it seems like
good. Good. It could be, maybe, we haven't talked about that, but in those sort of processes that we're doing here, these Susskind processes, we assume that it's really always entropy that's fed into that region and never outside that somehow would compensate that. That is clearly assumed, yes, absolutely. So I think Alex?
Perhaps you're going to talk about this, but it's like, does Hawking radiation mean that the generalized second law is full for the entropy And if, I mean,
Oh, okay. Well,
it makes sense thermodynamically a black hole tool, then
I'm actually not going to talk about that at all, but I hope that Daniel will tomorrow. Hawking radiation? No?
I mean, I just don't, how does that fit in design?
So the question is whether Hawking radiation could decrease the entropy of a black hole, and it can. It's the short answer. But it can do work, yes. Yeah, it's radiation. I mean,
So that brings me to this point number 8. It seems that the assumption in number 8 is that wherever you throw the thing is going to, in some sense, collapse into a black hole without spouting stuff out.
yes.
How can we be sure of that? How can we be sure that this is?
That there are processes like that at all, or? I think what's not necessary for the argument to succeed is that all processes involving black holes are like that. What is assumed, however, is that there exist processes like that for which this is possible. Supposing that there exist such processes, then I can do that. Whatever these processes are, I do this. I feed the black hole in a way that doesn't spit out or compensate the entropy in any other way. I think there's, from ideas like gravitational collapse and GR, there's some reason to think that, but I agree, it's not completely obvious that there are such processes. But
lowering, there is this analysis of Wald and company, lowering this, trying to lower something into the black hole.
yeah, so you...
Buoyancy forces preventing you from doing that without investing.
Yes. Yes. Look, at no point did I, for one, assert any of these assumptions I'm making here. I'm just trying to give you a sense of what sort of physically substantive assumptions have to go into an argument to the conclusion of a holographic bound. Maybe these are not strictly necessary. Maybe there's other arguments that could get you to the same conclusion. But that's the kind of arguments. That's a sort of a very generic, relatively simple argument structure here that is offered usually in the literature. Yeah, I like to think that this is a somewhat cleaner presentation of what you find elsewhere, but maybe I'm wrong about that. So I think Tim was first.
Can you just make a real quick comment on the rhetoric? Why is this a holographic bound? I mean, it's a kind of bound. Why are you calling it?
I'm gonna get to that. Yes. Why the choice of words here? For now, this is just the name of the bound. Okay. Let me. Or Wayne, something urgent?
No, continue.
No. Okay. Good. Now, some comments. The holographic bound, as then people like 't Hooft as the first person, and then Susskind, and following these two, everybody in string theory and maybe more people seem to believe now, is closely connected to another thing I'll put on the board here in a moment, the so-called holographic principle. If the holographic principle is true, that would explain why we would have a holographic bound. Because I think, and that is important, you should at least be a little bit surprised by the result now. You should be a little bit surprised that the entropy, the maximum entropy that you can pack into any region doesn't seem to be scaling with the volume of the region, but with the area of its surface. That is a counterintuitive result, it seems. That needs some further explanation. Now, if all physics, as it were, turned out to be like that, then maybe that would be much less surprising. That's the idea. Okay, and it seems to pose a challenge to classical field theory. Let me get to that in a minute. Here's pumping your intuition that you should be a little bit surprised. So think of not information, but this is from Bekenstein's popular article. He always talks about information as well. Scratch all of that, but think of just, physical systems with states, right? And certainly, these computer chips have their physical objects with states, right? And you can pack more computer chips into a volume, there's more states available there, right? Now, the more computer chips you pack, it seems like the more states there are. But the number of computer chips you can pack into the volume clearly seems to scale with the volume, not with the surface of that volume, right? So it seems there should be a point at which you can pack more states into that region than if it were the number of states would merely scale with the surface. That's why you should be a little bit surprised. Why is that not so? Tim?
Yeah, I never understood any of this. One thing that things are going to scale with is the mass.
Mm-hmm.
You expect whatever you're using to make this thing, if you throw in twice as much of it.
Sure, good.
You increase the number of states, well,
maybe.
In fact. Now, that's not a surprise. And the surface area of a black hole, A, scales with the mass of it.
Yes. Yeah, no, of course, that's what's going on in the background.
An argument that says, coincidentally, the surface area scales with it, but so what?
Yeah. So maybe what I'm saying is just saying in terms that I hope you understand in the way you want to approach this, is that to say that one would expect for a physical system that mass scales with volume, not with surface area.
But the problem is, when you talk about the volume of a black hole,
well, but yeah.
It's not, you're pretending that the volume is the Euclidean volume of a sphere that contains that.
Yes. No, of course, all of this is going on. Yes, exactly. But so forget about black holes. Put everything you know about black holes to the side. Just think about ordinary physical systems, like, iron spheres, iron balls, and you make them bigger. It seems that their mass goes with volume. So that's what I'm trying to say. That intuition seems to be violated now here. But of course, once you make the connection to black holes, it's much less surprising. And in fact, it's completely what you should expect. Anyway, this is then what Bekenstein says. Of course, it's seeped again in information theoretic talk, which is completely unnecessary. But he says, look, what fails in this way of thinking is the pile itself. It would collapse under its own gravity and form a black hole before that impasse was reached. The impasse meaning that where you would think you could pack more states into the volume than you should be able, were that number simply to scale with the surface rather than the volume. At that point, before you get to that point, he says, thing will collapse, black hole, then those sort of considerations, and you shouldn't be surprised that it scales with the surface area of the area rather than with the volume. Yes, Robert?
Yes, sir. Does the problem with letting go of the intuition has to do with the extensiveness of entropies? Not any more extensive when it scales with the area?
No. No, it's just, it's nothing more than the very naive idea that if you think about ordinary sort of matter and how it constitutes, the bigger you make the system, the more mass it has, and that seems to go with the volume of the system. It's really not much more than that. Anyway, thereafter, each additional memory chip would just increase the mass and therefore the surface area of the black hole in a way that would continue to preserve the generalized second law. Now, of course, that's a bit too quick, and if you're interested in some technical details why this is too quick, you should go and read Busso, who punches all sorts of holes into that sort of argument, but I'm not going to go through that, except to mention that a few points. First of all, what guarantees the applicability of the gravitational collapse? What is it that really makes sure that the pile of chips, if you want, or whatever it is, collapses before the impasse is reached, as it were? So really that's the more important point, supposing it does collapse at some point, what makes sure it collapses fast enough so that you could not exceed the amount given by the surface area? And of course, it could be either the generalized second law of our common sense ideas of entropy and information capacity could fail in some domains of gravitational physics. In fact, although as suggestive as much of that physics appears, it's not as if it's empirically well tested. I mean, this is just something that turns out to be really hard to do empirical tests involving black holes and, for instance, observing Hawking radiation or anything like that, because it's way too weak against the cosmic microwave background that we should ever hope to do that for astrophysical black holes anyway. Okay, fine. Or some of our assumptions could fail, etc., etc. However, and this is where you take out the magic rod, if there would be some basic features in future fundamental physics, then this would be perfectly natural to understand that something like an entropy bound would have to be, there would be a holographic bound. And that's the idea of a holographic principle. If our fundamental physics is basically governed, is basically holographic in that sense, then there would be a deep explanation of all of this. It would be perfectly natural. Now, what is the holographic principle here? So only just a rough idea. The idea is that a physical theory defined only on a two-dimensional boundary of a region, so this is really the boundary region, I guess, completely describes the three-dimensional physics of the bulk. So you can have a complete equivalence of the physical degrees of freedom that you have in a volume, in the bulk, and the physical degrees of freedom that you have on the surface. So it's like the hologram of the three-dimensional physics, the two-dimensional hologram, is just, it's dual to the three-dimensional physics. It contains exactly the same sort of degrees of freedom, exactly the same sort of physics. There's no distinction. There's nothing that's somehow left out of the physics in the volume if you take the complete description of what's going on at the surface. And this, of course, is the idea then that people take to even further speculative levels, talking about conformal field theory being dual to string theory in an ADS, in an anti-de Sitter space-time background, and the duality between a gauged theory, a theory not containing any gravity, and the theory containing gravity and the normal space-time, as a GR space-time, that is, and so on and so forth. That's the...
Replacing one mystery by a much bigger one.
Yes, exactly. But the nice thing about it is if you buy into this bigger mystery, then you can really explain the smaller one. No, I mean, I'm not kidding you. It sounds funny when you actually, put it as, expose it as such. But this is, I think, really what is going on.
Whenever you're going to buy something, read the small print. Whenever
You should
read the small
Oh, the small print. Yeah. Yes, that's even important.
The question that I was asking, should I buy it also for this context of, I mean, if I take it for granted in the context I was thinking, then I would have to come to the conclusion that whatever is occurring in this very small volume that I'm surrounding in the universe with this particular area exactly accounts for whatever is happening in this volume.
Yes.
Everything
Now,
can be codified in the surface.
of course.
I have a very hard time finding it.
Well, but you have to put yourself into the frame of mind of a string theorist. That is not mysterious at all, because of course you have all sorts of dualities between, the T-duality in particular, between the very small and the very large. So this is really, it's just the same physics again, of course, no surprise there. Now, look, I'm really not here to justify any of that, okay? But
Would really a string theorist say something that simple? I mean, take a teeny tiny black hole, a little tiny microscopic,
So,
and say, yeah, all the degrees of freedom in the entire universe fit on that.
Right. No, I should not want to be on record saying that string theorists would say that. No. So, but I don't know what they would say. I think a more sensible way would try to articulate, say, look, no, there's certain privileged volumes and privileged boundaries, and this is only going to be valid for certain relationship between certain bulks and certain boundaries and not in general, and so on and so forth. Rasmus.
So just to defend ADS-CFT a little bit. So Hooft makes this conjecture in 1993. It's completely speculative. 5 years later, we discover a realization of this principle in the form of ADS-CFT. At least that is curious circumstance, I would say. So it's just saying there could be something to it.
Oh, yeah.
That the holography initially is conceived without any regard for string theory.
Yes.
And now we find it
So,
in the form of ADS-CFT. It's just thinking about it a little bit against
yeah.
this
No, that's
ADS-CFT
true.
fashion.
That's true. Okay, good. I certainly accept it as it's possible. I don't have an argument that it's impossible. And it's true that 't Hooft, when he originally formulated the holographic principle, clearly was not coming from string theory. He came from, as we will see if we get there, from more basic considerations concerning the unitarity, really, of quantum physics, of a sort of a scattering matrix that takes an initial state to a final state that should be unitary. And if you accept unitarity and some other basic ideas I put at the beginning, then you seem to be almost forced into something like at least a holographic bound or some sort of deeper holographic principle, perhaps. So that's where he came from. But then, of course, once Susskind takes over, then it goes into string theory, and then Maldacena conjectures this specific form of a holographic theory, and then this takes on a life by itself. Travis.
Just that even more extraordinary than that, they had a theory that implemented the holographic principle. They explicitly calculated the number of microstates in a black hole and got the exact right answer.
Well, okay. This is going further into territory that I didn't plan to go into. There are these calculations, but they are relatively limited because they concern so-called extremal black holes, which Daniel hasn't talked about, but these are black holes which either rotate so strongly or are so strongly charged that relativists, anyway, don't think that they represent any really realistic form of black hole. And for those very limited classes of black holes, you can do the state counting and do the argument that you mentioned. There seem to be recent indications that you can relax this a little bit and not just look at extremal black holes, but near extremal black holes, which are a little bit better. But so there are some ideas, but they're far from fully general. Anyway, Joanna, you had a question, right?
Yes, I'm sure it's a good question. Not all things scale with area, so why should this reasoning be applied to black holes and not to these other big things in physics which scale?
So you're questioning the holographic principle, right? Yes. No, I mean, this is, I take it what Shelley meant.
Itself, but you said you didn't explain how should we go from this principle to black holes, but my worry is very simple, that in physics we have many things to explain, black hole entropy scales with area, some other things scale with volume, for example, so why we should apply this kind of reasoning to black holes. Maybe it's impossible to explain it without technical things.
Right. no. But I do take it that what you're asking is why should we think that fundamental physics is holographic in this sense? Just from one sort of instance, as important and central as it may be, to sort of infer that all of our physics should be like that seems to be a leap. That requires at least further justification. And I take it that Shelley was referring to that. You replace a small mystery with a much bigger one, not just why this particular proposition is true, namely the holographic bound, by the bigger question of why fundamental physics in general, concerning all quantities, everything that's of interest to us in physics, should be addressed or articulated by holographic theory. Or did I not understand the question? Or
Perhaps it is not exactly what I wanted to say.
okay.
Rather, building on what you have said, isn't it empirically disproved that everything works like this? I mean, what I have in mind is really simple, that we know from physics quantities which scale with volume. So what, why they scale with volume?
So, okay.
And black hole entropy scales with area.
So are you...
This principle isn't possible.
So are you saying that there are counterexamples to the assertion that the holographic principle should govern fundamental physics?
Yeah, she's saying that.
Okay, good. Yeah. That's something to keep in mind, absolutely. So that may be way too strong as a result of considerations like that. Okay, good. So how much time do I have? Because if we're honest, I think I'm getting close to my full hour that I said I would need. Okay, well, very quickly. If you do more sophisticated state counting than what we did initially in field theory, then you can do all sorts of things. You assume that you don't have an infinite number of degrees of freedom in any volume, and you can assume that they're all energetically bounded from above and below, so you can have a finite, well-defined number of degrees of freedom, even in something like a field theory. If you take what Busso says, including gravity, at least in a very crude and minimal way, but even if you do that, there is a relative simple argument that people can follow on my slides when I put them, send them to Mario to put them up on the website, that the number of degrees of freedom based on something like a field theoretic approach should scale with volume, or with volume times some number or something like that. Whereas in a holographic theory, you wouldn't expect that. You should expect it to scale with the surface of where the holographic physics is encoded completely. So we have two different approaches. It seems like at most one of the two can be true. Both are out because they give contradictory answers. Should we believe A? Should we believe B? Or as a philosopher, I would add the third possibility, should we believe neither? That seems clearly a logical possibility too. Now, Busso says, well, look, here's an argument why you should think that field theory overcounts the available degrees of freedom. And the argument is basically invoking gravitational collapse. If you pack degrees of freedom too densely, then the states that are necessary to go beyond the holographic bound are states which are too massive to be gravitationally stable, so there's gravitational collapse. That's basically an assertion, really. It's not shown in any detail. Now, even if you accept that, that would at most show that you shouldn't believe A. It certainly doesn't establish that you should believe B. Okay? And he acknowledges that much. Okay, good.
Can I ask a question about that? So is this principle only meant to apply to black holes? So, I mean,
well,
so my follow-up question is there a conceivable experiment that we can do on Earth? Or do we have to travel to the center of the galaxy to answer this kind of?
Oh, I don't even know whether the center of the galaxy would answer that.
It seems like these two approaches does have experimental consequences. Just like, is there possible to perform an experiment?
So you would
ultimately that should decide. Not
I mean, in principle, yes, because in principle we could do thermodynamics with very, very massive systems, and perhaps if we do that, we can invalidate one or the other. But in practice, this is far from the sort of the systems we can experimentally control. So I don't know of any way to do that. Okay, anyway, here's an argument that I'm going to skip that, if you believe in unitarity, you should believe in the holographic bound. But I'm going to skip that. That was 't Hooft's original motivation, because he believes in unitarity very much, and therefore, together with assumptions about black hole thermodynamics and about gravitational collapse, feels himself compelled then into the conclusion of a holographic bound. Okay, now, based on these sort of considerations, here's a somewhat more cautious formulation of the holographic principle, namely that a region with boundary of area A is fully described by no more than a quarter of that surface numbered degrees of freedom, or if you prefer the information theoretic way of putting it, 1 bit of information per Planck area. And Bousseau says a fundamental theory, any fundamental theory that is going to underwrite our standard model of particle physics or general relativity should incorporate this counterintuitive result. In fact, what he says is the holographic principle may have been an audacious concept to propose. But in light of the intervening developments, such as the generalization to geometric terms which are more native to general relativity and the covariant formulation of entropy bound, and he believes a particular response to the black hole information loss paradox called black hole complementarity, and I'm definitely not going to go into that, but just to warn you that this is highly challengeable as even as a problem, let alone as a solution. He thinks it has become difficult one to reject. So it seems like within just a few years, everybody in fundamental physics should have been convinced by now that the fundamental theory is going to be holographic principle. I am sure that you can judge from the tone of my voice that I am skeptical of that conclusion, and I believe so should you be. But my goal today was not so much to challenge these sort of ideas, but to give you a sense of how, from black hole thermodynamics and extending some of these ideas, you can get to places where physicists in fundamental physics, in string theory in particular, but in quantum gravity more general, speculate these days. Okay, one final thought, if I may. We have started, so you might have the following worry, that the whole story is not just possibly false, but is inconsistent and therefore necessarily false. I don't think that's quite right, but to see what the potential inconsistency is, let me allow you to show you this final set of considerations. First, we have used, well, we haven't yet, I guess that's maybe for tomorrow, we have used quantum field theory on curved space-time to derive black hole entropy, in particular to derive Hawking radiation and to get the full black hole thermodynamics. This is the sort of theoretical background that we need. From that, together with some other assumptions, we have then argued to the holographic bound. The holographic bound we have then used to reject quantum field theory on whatever space-time background, because we said quantum field theory is going to give us a wrong way of counting the states. So you might think, like, what the hell is going on here? Do we have something like field theory, a derivation from that to a particular proposition, which together with other propositions is supposed to support that, which undermines the original vantage point? Oh my God, that would be bad. Well, that would be bad, but I don't think it's quite as bad as that. Of course, it could be that what we've learned when we do physics like this, when we've argued from this to here, that indeed we have discovered a more fundamental truth about fundamental physics. And we would have to reject field theory as a way of doing fundamental physics. But even if that's the outcome of this, it doesn't mean that the train of thought that has led from less fundamental physics to more fundamental physics is therefore invalidated. It could still be that in some appropriate limit, effectively, in some sort of approximation, for much of the physics that we know and love, this is just fine. However, for fundamental theory, this is really what's the unmitigated, unconditionalized truth. Now, for me to buy into that, it would take quite a bit more than what's been given to me so far in the literature, but at least I accept that this would not be an inconsistent possibility. Thank you very much. So I don't know how much time we have.
Some more. So independent on any scaling, how seriously can one take the idea that in a finite region the number of states is finite? Or how seriously is this idea taken? How seriously can one think about it?
Well, as a possibility, I think it should be taken seriously. If that's the only thing you're asking, then I think, yes, you should definitely consider this a serious possibility. However, it's a serious possibility that in order to believe requires you to make some substantive assumptions about the physics that's relevant for this. And of course, one of them could be wrong. As we learn more about fundamental physics. In particular, as we learn more how to combine our best physics of the constitution of matter with gravity. If we incorporate that, maybe things go very differently from the way we have anticipated, in which case some of these things may fall apart and then I no longer have that ground. But as a possibility, I think it's perfectly serious.
So what I'm thinking there is, wouldn't I need just the same justification to assume that the number of states is infinite somehow? I mean, it's not, I have done an empirical access somehow to this question, if there's infinite or finite number of states.
Maybe not whether it's infinite or finite, but if you say it's finite and I give you a way to compute it using the holographic bound, that's the most states in a way that you can pack into a region, then maybe you could do an experiment in principle to show that no, I construct a system where I pack more states into a region like that. So you could, in that sense, you could falsify the holographic bound without thereby establishing that the degrees of freedom you pack in a region could be infinite.
Hold up.
I just wanted to make a point that people will know. In loop quantum gravity, the quantization of area is actually one of the fundamental consequences. And actually, for non-external black holes, we are actually able to recover the bound up to the factor diversity parameter, which is the 1-3 parameter.
That's right. So there's a sense in which the derivation of the Bekenstein-Hawking formula in loop quantum gravity is more general than those in string theory because it's not just applicable to extremal black holes, but... Sorry?
This is true for any region of spacetime. Every region of spacetime has a discrete area, has a discrete spectrum with a minimum value.
That's right, yes. Yes, absolutely. But it does, it's up to a parameter that has to be put in by hand or by some additional sort of argument.
Which there are many arguments.
Yeah.
Excuse me, but that's the difference between saying how many degrees of freedom you have on the surface and something else is saying how many degrees of freedom are surrounded by the surface.
Oh, yes, yes. So I don't think that loop quantum gravity is holographic in that sense. Correct me if I'm wrong, but I don't think it's holographic in that sense. But
very definite method for counting area states within a
exactly. Yes. Exactly.
And that live on that boundary.
That's right. And
those that live inside.
Precisely, and that can be thought to underwrite black hole thermodynamics, but not holographic physics altogether. Yes.
Maybe I'm doing it too naive reasoning, but I find very natural there should be a finite number of states in a bounded region.
Yeah.
Because it's like radiation in a cavity. Okay, so I have a number of a discrete set of normal modes. Then I expect to be a cutoff of the energy that is of the mass. So that I don't get this idea that quantum field theory necessarily predicts an infinite number of states.
No. So that was just the original.
The mass of the energy.
There will be a maximum energy.
Maximum mass, something like that. Why is not unreasonable to expect that?
No, I didn't. I hope I didn't say it's unreasonable. So,
on Lorentz, you take something that has some energy, you go to a different frame, now it's boosted, and the energy has gone up. So you want to put also a cutoff on the boost that we can do.
So if you have a finite
blank scale. There should be a scale in the mass that should bound the number of states.
Look,
it automatically commits you to breaking Lorentz value.
Well, maybe there's a way to do that without breaking covariance, but it's not clear how you could do that. I mean, in a way, that gives us the deeper tension between quantum field theory and general relativity, and how are we going to negotiate that?
You will have to pay a price for that. I'm saying it's ruled out.
Yeah, it's certainly not ruled out. You may even think it's natural. It's certainly a serious possibility, absolutely. And maybe, you shouldn't think of quantum field theory with sort of containing a harmonic oscillator at every space-time point which has unbounded energy and access to infinite number of states. Maybe that's just wrong. Maybe there is bounded energy. It really has only a finite number of states that are accessible to it. And maybe we should really, once we start to think about gravity more carefully, we can't really think that we have an infinite number of harmonic oscillators in a spatial region, but only one per Planck volume or something like that, in which case there are perfectly reasonable reasons to think that there's a finite number of degrees of freedom in a space. So I'm not denying that. But from that to the assertion of a holographic principle is still a very, very substantive step. And yeah.
So just to jump in on the idea of a finite number of states for quantum field theory. So it was already mentioned that in quantum mechanics, if you take a finite volume and energy cutoff, you have a finite number of states. In quantum field theory, actually, something analogous also holds.
Okay.
So you take a finite volume of space-time, and in your Hilbert space, you take an energy cutoff. You may still get an infinite dimensional Hilbert space, but the operators that you can perform locally can be approximated with very strong sets by finite dimensional Hilbert space.
Yeah.
So it doesn't quite give you a measure on your phase space that allows you to define an entropy in that sense, but there is some finite dimensional properties coming in in very precise sense that can be used.
Okay.
So basically in the continuum limit of quantities.
Excellent. Thank you very much. So, you know, that gives us another really good reason to think that, yes, it's finite. But again, even if it turns out to be finite, that does not imply the holographic bound, let alone the holographic principle, of course. I mean, that's quite a different thing to assert, because it could then, of course, still be the case that for any system, you know, it really scales with volume, not with area, and you can pack them so densely that you can have systems that do not gravitationally collapse under their own mass, and therefore, you know, would violate the holographic bound. Yeah.
Thank you very much.